Thank you all for joining. The topic of my presentation is characterization of near surface material, that is soils, which is an important aspect towards reliable simulation of ground motion. So here is the outline of my talk. The objective is to highlight the lessons learned in applying a recently developed stochastic full waveform inversion algorithm to characterize a geotechnical site from geophysical measurements. Uh, I will start with summarizing the algorithm. It is essentially a minimum variance framework, which relies on the Bayesian uh, interpretation of the parameters, but a few components of the algorithm has been adjusted to suit this method for computationally efficient geophysical imaging. These components are a Gaussian mixture model for parameterization of soil properties, a generalized polynomial chaos approach for representing the PDF of these GMM model parameters, and a non-product quadrature rule for evaluation of high-dimensional expectation integrals. Next, I will exemplify this algorithm in estimating P and S wave velocities of soils at a 60 meter by 60 meter geotechnical site up to a depth of 40 meter. Through this exemplification, I will highlight the lessons learned as well as comment on the scalability of the algorithm for larger scale geophysical imaging. So here is uh, the flowchart of the algorithm. It essentially fuses sparse experimental measurements with finite element simulated measurements using a minimum variance framework. The finite element simulation relies on prior assumptions, uh, which are then used for simulating the geophysical experiment and fuse with experimental measurement. So here Z is the real measurement and H is the simulated measurement. The superscript epsilon, the superscript plus denotes posterior, and the superscript minus denotes the prior, and k epsilon is the expected operation, and capital sigma is the variance covariance matrix, and k is the Kalman gain matrix, and r is the noise covariance matrix. Now, for FE simulation, we need to parameterize the soil properties in the domain of interest. Soil deposits exhibit spatial variability. We see non-uniform layers and lenses within layers. So uncertain soil properties are increasingly being modeled as random field. The conventional random field parameterization uses the Carhonian Loeb expansion for spatial discretization. It is mathematically optimal, but requires repeated use of very large-scale eigenanalysis. So to bypass this issue, we used Gaussian mixture model for parameterization of random field soil properties. This Gaussian mixture model comprises of two types of functions. Hat function mimic horizontal layering of the soil deposit, and Gaussian function mimic the presence of non-uniform layers and lenses within the layers. In the equation to the right, this alpha denotes the hat function. They are one-dimensional function, and capital gamma is a three-dimensional Gaussian function. In the figure to the left, I have tried to show how these functions work. The top row shows how does the Gaussian hat function work. So the top row of figure just have hat functions, one-dimensional hat functions, and it creates uniform layering of the soil deposit. And the figure, the middle row actually demonstrate when we throw in a Gaussian function. I'm using my mouse to show that what happens if we add a Gaussian function into the mix. So it allows for mixing of information between layers. And you see what is the resultant. It's kind of a non-uniform layers, and we can see even lenses within these layers. Now, these parameters of these Gaussian and hat functions are both random variables. So the bottom row here, it shows when you use another set of Gaussian parameters, then we get a very different type of soil deposit here. So now the minimum variance framework will tell us among all possible values which one is the true for the site given the measurements. So the minimum variance framework gives only the mean and the variance. That means up to the second order statistics of the posterior estimates. Then we use here a generalized polynomial chaos theory to approximate the PDF from the second order statistics. It is important to mention here, these PDFs are all approximate, coming out of the generalized polynomial chaos theory. The mean and variance are coming from the minimum variance framework. Now, this minimum variance framework involves two types of expectation integral. One is the stochastic collocation integral that is needed to estimate the statistics of the finite element simulated measurements. Over here, I have shown that with this is finite element displacement u, and epsilon is the expectation operation. So expected value, and then there are minimum variance integrals like sigma theta h and sigma hh. For example, here I have shown how sigma theta h will look like. So I have used some numerical quadrature rule to express means how we are going to evaluate that numerically. Now, as you have heard, there is a problem with evaluating these integrals. They suffer from curse of dimensionality as the number of random variables grow. That means the dimension of the problem grows. For example, if we take the example of Gaussian quadrature rule, so which rely on tensor product of one-dimensional quadrature rule. So for example, if we have for a one-dimensional problem, so that means one random variable in the system, if we need 5 points, then for a five-dimensional problem, that is for five random variable case, we need 5 to the power 5. That means 3,125 finite element runs. Those means data points. That's an exponential growth. So to bypass that, we use something called conjugate uncentered transformation. I'm not going to get into the details of the mathematics. It was developed by my collaborators. The details are here in this paper, but it is nothing but an extension of the conventional uncentered transformation, which satisfies additional higher order moment constraints. So for example, here for this five-dimensional problem, where Gaussian quadrature rule would have required 3,125, cut would require only 314. Uh, so now getting into the example. So here are the details of the testbed site and the geophysical experiment. The site is a 60 meter by 60 meter parcel of the niche at UCSB Garner Valley site. And the geophysical experiment was performed by the UT Austin group over there. So these red squares, they denote the source location, and the black circles denote the receiver location. So at each of the source location, the T-Rex seeker, the UT Austin T-Rex seeker was placed and uh, was used to excite the ground, and at all the receiver location, the soil responses were recorded. So shown on the right, top right, the source number 3, that is here, the ground excitation in terms of the time series and the Fourier spectrum of that ground excitation. As you can see, it was basically a sharp signal with frequency content from 2.5 hertz to around 12 hertz. And in the bottom, the soil responses, bottom right, the soil responses at receiver 10 and the receiver 2 are shown. As you can see, there are two color I have used here, red and blue. The red one, the blue one is the raw data, and the red one is the recorded or the process data. To the UT Austin group remove the noise and share the process data with everybody. Now, if a simulation will require prior assumptions, for this example, we used uh, local geology and PN suspension logging available at a nearby site for the prior assumptions. The figure on the right shows the VS and VP measurements available at a nearby site. As you can see from this plot, from this PS suspension logging, there are two horizontal layers up to a depth of 40 meters, a relatively loose sand layer up to a depth of 20 meters, and denser sand and weathered rock below. And the local geology tells us that the site is located very close to Lake Hemet, so the water table is expected to be shallow, even though there will be some seasonal variation. Accordingly, to parameterize Vs, the shear wave velocity, we use three hat functions with centers at 0 meter, 20 meter, and 40 meter. And for Vp, we use two hat functions with centers at the surface and at the depth of the water table, below which it is represented as a function of Poisson's ratio and Vs, because below water table, the P wave velocity is governed by the Poisson's ratio, which is incompressible, so close to zero point 0.5. So here are the prior assumptions for FE simulation. The figures on the left shows 3D profiles of the mean and standard deviation of VS, and the bottom row, the mean and standard deviation of VP. And on the top right, the correlation structure is shown. Correlation structure is basically, it's coming out of that Gaussian mixture model, those mixing parameters, which we have denoted here with Lx and Ly. For this example, we have assumed both to be the same. So that means X direction and Y direction. So this is a 7-dimensional problem here. So the random variables are Vs0, Vs20, Vs40, Vp0, Hw, which is height of water table, and then nu, Poisson's ratio below water table, and the mixing parameters. So here I have shown the FE simulated prior mean uh, with, with the experimental measurements at all the receiver locations. There are 35 receivers. One of them malfunctioned, so I am not showing that. So there are basically 34 receivers. The FE simulation was performed using conventional approach in OpenSeas. Uh, 8-noded brick elements, we used a Rayleigh damping of 2%. And the mean was calculated using conjugate uncentered transformation. Only 551 FE runs were needed for the 700 for the 7-dimensional problem. As you could see, there is a lot of mismatch at all the receivers' location. So the minimum variance framework will adjust this mismatch and inversely calculate the soil parameters. So we tried first a time domain inversion. So at all the times, we tried to, that's the feature vector we used, but you can see the results are shown on the left in the table. Something went wrong here. So you can see the Poisson's ratio is 0.56, which is unrealistic. The water table was almost 30 meters below the ground surface, impossible for that site. The reason was that the time domain inversion failed, didn't work due to failure of the ensemble averages of the model output to preserve the physical characteristics of the dynamical system. Then we tried frequency domain inversion. Uh, it gave us good results, actually. As you can see, both Poisson's ratio and water table. On the right, we have shown the top right, the table shows the outcome of this analysis, the frequency domain analysis. And in the bottom, we have shown how the posterior and prior PDFs of these Gaussian mixture model parameters are compared. As you can see, most of the cases, things moved, but to, to, to get what happened, basically how they compare. So here I have plotted the posterior mean versus the experimental measurements at all the sensor locations. As you can see, there is reasonable match at most, but not all the receiver locations. So we were asking the question, can you do better? Why it did not work that well? So to look at that, uh, we we were thinking whether the prior assumptions were good enough. You have heard from the previous speaker, Professor Yusuf Marzouk, that the prior assumptions are also important. So in understanding whether the prior assumptions were good enough, we plotted the realizations of simulated peak frequency with the experimental measurements at all the receiver locations. So the black line is the experimental measurement, and these green dots are basically all the 551 realizations. Ideally, the realization should center around the measurement, but at most of the receiver locations, they are not. So then I looked at the amplitude corresponding to the peak frequencies. They also did not behave ideally either. So we were thinking, can we do a better job? The Fourier amplitudes and the peak frequencies of simulated measurements should be smaller. So these simulated measurements should come down. They should center around the experiment. But the question is, which parameter to adjust? We're still talking about the prior. So we did some sensitivity analysis for improving the prior assumptions. We calculated the Pearson correlation coefficient between prior theta and FE simulated Fourier amplitude corresponding to the peak frequency at each receiver location. And based on that, say for example, from this figure here on the top left, we can see that theta is negatively correlated. So increasing theta is expected to reduce the values of the Fourier amplitude. So, and similar observations we could uh, get comparing theta 2 and theta 5. So accordingly, we improved the prior and redid the posterior analysis. So that in the top, we have shown the improved posterior estimates, and at the bottom, we have shown the original posterior estimates. So they are very similar, except two cases. VS naught and VP naught moved the most, but VS naught increased and VP naught decreased. But you can see that VP naught here, the uncertainty in the posterior estimate increased also. So here is the comparison in the frequency domain between improved posterior mean and the experimental measurements. Uh, they did better job compared to the original case. So here, now it's the time domain comparison at all the receiver location. So the updated prior for soil parameters lead to finite element ensembles that better compare measurement data due to their subset, and hence leads to more accurate soil
Hello?
parameter
You
estimates.
have 1 minute.
Sure. So here we have shown the posterior profiles, the mean of VS here and the standard deviation of VS there. And in the bottom, the VP, the mean, and this is the standard deviation profile of VP. You can see non-uniform layers and lenses within layers. Now you can see the uncertainty in VS. It's large when we compare it in terms of coefficient of variation. It is large at the surface, and as we go deeper, it is getting smaller. Now for VP, consistent with that of partially saturated soil, pockets of larger values, albeit with large COVs between surface and the water table. And here, these are the posterior correlation structure. We can see in the horizontal direction, it fluctuates from positive to negative over a long distance. That means intermixing of information between layers over the length of the site in both the direction. And the structure for VP and VS were similar, but there exists some difference due to more uniform nature of P wave velocities of saturated soil. Now, a few comments on the scalability of the algorithm. Because of GMM and CUT, uh, this algorithm can be used for larger scale geophysical imaging without prohibitive computational cost. GMM bypasses large-scale eigenanalysis by approximating the eigenfunctions of KL expansion, and CART alleviates the computational burden associated with high-dimensional expectation integrals. However, the algorithm uses conventional finite element method for numerically simulating the geophysical measurements. We need an efficient approach for modeling wave propagation through soils, ideally a reduced order model, or as you heard from previous speakers, a surrogate model that will be needed for larger scale geophysical imaging. Thank you.